Hey everyone, let's start slowly so we don't push the limits too much in terms of time. So we have the pleasure today to have Link here, Lei Ying today. So, of course, we all know him. He's a full professor here at the X department. Needless to say, now he's an IEEE Fellow. He has taken several career awards like NSF or DTRA, I think it is called. Yes. The defense threat response, something like that.
Right. Yeah, reduction agent.
Reduction and multiple also best paper awards, almost one every year or every 2 years. So today he's talking for us about constrained Markov decision processes, and yeah, we look forward to the talk.
Thanks, Valesius, for the nice introduction. So today I basically talk about our constrained MDP problems, and in particular, try to understand is CMDPs fundamentally different from MDPs, or are the problems harder, why they are harder, and how much harder they are, okay? So first of all, for those of you who may not be very familiar with MDP, just very quickly, what is a Markov decision process, right? So let's consider a simple example. We have an episodic MDP, and you have agent. The agent need to take multiple steps. So starting from step 1, the agent can choose an action from one of the multiple actions. Then after the action is taken, then the agent will move to the next state in step 2, and that transition is probabilistic. So here with probably 0.8, the agent will be in state 0 at step 2, and will be in state 1 at with probably 0.2. Okay. Then together with the state transition, the agent also receive a reward. That reward is depending on the state and the action. Okay. Then the goal here is to try to find a policy. Policy is a mapping from the state to action, tells the agent which action to take in what state. Try to find a policy such that maximize the total reward it received over these H steps. Okay, so again, since the model is probabilistic, so the agent try to maximize this expected total reward. Okay, so why we are interested in MDP? Because MDP is a very powerful mathematical tool to study many engineering systems. In particular, it is a foundation of reinforcement learning. What is reinforcement learning? Where we talk about agent interact with the environment, the agent takes an action, then receive a state and a reward from the environment. Reinforcement learning aims at learning the best policy by the interaction, right, from the data. Applications, there are a lot of applications. For example, something we are very familiar with, AlphaGo. It's part of the reinforcement learning problem. And autonomous driving, people talk about using reinforcement learning to use in autonomous driving, ride sharing, 6G plus, and so on. Actually, many people believe reinforcement learning is one of the key technology for us to move to a general AI. Okay, so instead of using like a deep neural network just do classification, say this is cat or dog, to extract knowledge from the data, reinforcement learning actually help us to extract strategies, policies, right, from the data. Not just the knowledge, but also tell us how to make the decision, which decision is good, which decision is bad, and like human, more like a human to make decisions in various systems, right? So that's why there are so many interests in reinforcement. But it's also fair to say, like, although like it's a belief, like reinforcement learning is a key technology to enable the next generation AI, and we have seen tremendous success of reinforcement learning in like board games, video games. But if we look at our engineering system, right, look at the application or implementation of RL in the engineering system, we only see very limited success, right? One of the reasons I believe is because most engineering systems are very complex systems, right? Like autonomous driving, like power system, like communication system. They are very complicated and complex systems. So in those systems, when we design a policy, the goal should not be just to maximize some reward, right? So what we need to have is not a single-minded policy. The policy has to obey or have to operate it under various operational constraints. The constraint could be like power limit, could be the budget constraint, and many other constraints, safety constraints, and so on. Okay. If we look at that kind of the problems, and if you look at the like the traditional MDP framework, you can realize the traditional MDP framework only tells us how to maximize the reward, but does not put the constraints in the problem, right? So that's a problem. So how do we deal with that, right? Here, just an example, like in autonomous driving, if we look at this application, if we think about the reward is how long does it take for the car to get point A to point B, you immediately realize that reward is probably not even the first order consideration of designing the system, right? Probably the first order consideration is in fact the safety. We have to make sure the operation is safe before we start to maximize the reward, right? So how do we deal with that? The mathematical tool to deal with this type of the constrained reinforcement learning problem is to use constrained MDPs. So what is constrained MDP? Again, use this very simple example. So now instead of besides just getting a reward signal after taking an action, let's say the agent also get another signal called a utility signal after taking the action. So originally in MDP, the agent just receive a reward signal. Now it will receive two types of signals, reward and utility. Okay. With that, now we can formulate the problem as this constrained problem, such that the goal here is to maximize the total reward, subject the total utility is loss greater or equal to this row. So we have this constraint here. Okay, so this is just a simple example. You can imagine if you have multiple constraints, then you can like the agent can receive multiple these constraint signals or utility signals, and you can put the multiple constraint there. Okay, so that's become a constraint MDP. Okay. So the next question is, okay, so now I go from MDP to constrained MDP, so what, right? Is the problem fundamentally different or not? So to answer that, let's look at just a few like thought process, right? The high level ideas to see why they are different. Any questions before I go to talk about the difference? Okay, so for those of you who are taken classes on MDPs or dynamical programming or reinforcement learning, right? You probably know if I want to pick one equation as the most important equation for these areas, right? The equation you probably will pick is a Bellman equation, okay? So this single equation is behind dynamical programming, MDP, and the reinforcement learning is the single equation we try to solve, okay? And why this equation is so important and why it's so nice, like in the unconstrained setting, this Bellman equation or principle of optimality tells me if I want to go from A to B with a minimum cost, okay, then I arrive certain intermediate step, let's say here, okay? Then what I need to design for the policy to minimize overall cost, if I already reached this stage, is I don't need to worry about the future. I just need to worry, I don't need to worry about the past. I just need to worry about the future, right? I only need to worry about what is optimal actions to take from the current state to help me to get to the final destination. And what actions you have taken in the past doesn't really matter here. Okay, so that's also called the principle of optimality. It says if I have optimal path from A to B, if I take any subpath, that subpath has to be an optimal solution for a subproblem, right? Because otherwise you can find a better path here. You can connect that better path with the original subpath here to get a better solution, okay? And it turns out, if we translate it into the Bellman equation, it says the Q value at state S and U equal to the reward you receive plus the best future reward you can get, or best Q function you can get from now on, okay? So that helps us because now when we kind of learn the best policy, we just need to look at this Bellman equation. And we use the difference between the left-hand side and the right-hand side as a loss function. For example, in Q-learning or like deep RL, and by minimizing this loss function, we can identify the best policy. Okay, so this single equation is at the center of all the reinforcement learning algorithm. Okay, so now let's look at the case if we have constraint. what happens, right? If we have constraint, then the things are different. The different in the sense, let's say we have budget constraint, right? So now, how do you go from the origin to the current state matters here? Because how much, let's say, budget you have consumed, limit what future paths you can take, right? If I only spend like a small amount of budget at the beginning, then at the current state, I have a lot of flexibility and a lot of the budget to expand help me to get to the destination. On the other hand, if I already spend a majority of my budget to get to the current state, then the number of options I have, the number of paths I can take to get destination become limited. So that means in a constraint problem, not only the future matters for me to make the decision, the past also matters for me to take a decision, right? So the past and the future is coupled. I cannot have this very nice single Bellman equation to describe what the optimal policy has to satisfy, right? So therefore, I cannot use that, for example, as a loss function for my algorithms, right? So that's the fundamental difference. And to further illustrate the difference between constrained and unconstrained case, let's consider another very, very simple example. So this is a simple banded problem with two arms. Here, two arms represent two workers. I have a task coming. Worker 1 can work on a task and give me a reward of 0.7. Worker 2 can work on a task and give me a reward of 0.9. Okay. So now, which worker to pick when the task comes in? No constraint. What's the answer? I go to the worker giving me a higher reward, right? It's a 0.9. It's a greedy action to take. So now if we have constraint, let's say I don't want this good worker to continue to work on the job all day and all night while the other worker is idle. So I impose a fairness constraint. Say each worker should receive at least 40% of the workload. Okay, so now what is the solution? The solution, again, here is very straightforward, is I assign 60% of the job to worker 2 and 40% job to worker 1. Okay, so what's the difference between these two scenarios? If you look at your decision space, right? For the unconstrained one, we are just picking one of these two decisions, right? Picking 0 or 1, right? Which worker is better? So it's a greedy decision. But as soon as I impose this constraint to this problem, now your decision space go from discrete and finite to continuous, right? So now become a number, a real number between 0 and 1, and the policy becomes stochastic. Okay, so your decision space immediately become much, much larger and become much more complex to solve. Okay, so that's also the fundamental difference between unconstrained MDP and a constrained MDP. For MDP, in most cases, you can find a greedy policy, which is optimal. The greedy policy, for example, it can based on the Q value, called Q linear. You just look at the Q value, pick the best one. But for unconstrained, for the constrained case, it often is a stochastic policy. So which means that any greedy policy will not be optimal, and you have to figure out the stochastic policy. Okay, any question? Okay. So now let's look at what we can do in the case of CMDPs and what will be the efficient algorithms and what people have known and what are unknown in these scenarios. Okay. So let's look at the episodic case, a very simple, I mean, it's one of the MDP. So we can have like infinite horizon MDP, discounted MDP. Here, let's focus on episodic MDP. So for each episode, it has H steps. The agent go from step 1 to step H, then the episode terminates. Then we start a new episode and so on. Okay. Let's also focus on the tabular setting, such that the state space is finite and the action space is finite as well. Okay, so that enables us to establish some theoretical result. Okay, the goal here again is to maximize the total reward with the constraint the total utility is larger or equal to 0. Okay. So what do we have known? So this problem is not new. CMDP is not new problem, especially in the case when the Markov chain, the model is given. So if the kernel is given, there's been a lot of extensive research on this topic already. Okay, probably the most popular approach for solving this problem is to use linear programming. Okay, so how do we use the linear programming to solve that? Let's define this Q HXA here, QHXE here to be the occupancy measure. So what is the occupancy measure? Occupancy measure basically tells me under a given policy, what is the probability the agent will be in state X at step H and taking action A. Okay, so just the probability of that, right? So if that probability is given, then we can use that occupancy measure to write the expected reward as the probability times the reward you receive, right? That gives you the average reward. And then we can also write the constraint as the probability times the utility you receive, and that should be greater or equal to 1, okay? Then it's a Markov chain, so it had to satisfy the global balance equation. So the occupancy measure had to satisfy this equation. So the probability times the transition should give you the next probability measure, okay? And of course, the initial condition has to be satisfied, and all the occupancy measure, their probabilities should be greater or equal to 0, okay? So you can see now if we look at this optimization problem in terms of occupancy measure, the objective is linear, all the constraints are linear. So it's a linear programming, okay? Not only is a linear programming, and also the occupancy measure has a 1-to-1 corresponds to any stationary policy. So first of all, any station policy will yield a valid occupancy measure. And second, if you solve an occupancy measure by solving this LP, then you can recover the policy by this simple equation. So what is occupancy measure? That's the probability the agent is at step H in state X, then take action A, okay? And the agent has multiple actions to take. So if you look at this ratio, that tells you the probability of agent take action A at step H in state X, okay? So if you just use this equation, and that gives you the policy, right? So every occupancy measure uniquely map back to a policy as well. Okay, so basically this LP optimizing over this occupancy measure is the same as optimizing over the policy space. Okay, so that's therefore if this transition kernel, the MDP is given, then we can or the reward function is known and the utility function is known, then we can use the LP to solve the problem. Okay, that's again, it's not new. Back in 1999, we already know how to do that. So now there are interesting questions, like driven by the tremendous amount of interest in machine learning, in AI, and in reinforcement learning, is to solve this problem when the transition kernels are unknown, right? For real large systems, it's impossible to know the transition kernel, right? So what happens if the transition kernels are unknown, reward function and the utility function are unknown, and we only have data, right? How do we solve this problem? In particular, how to solve this problem in an online fashion, such that we start with some policy, and we apply that, then we get some data, we update the policy, and continue to collect data, update policy, and so on, okay? So how do we evaluate the performance, right, in that online setting? In the online setting, we usually evaluate the performance or use 2 criteria for CMDPs. One is called the regret. What is the regret? Regret is the difference between the reward you receive under the optimal policy versus the reward you receive under the policy you are using, right? So that's the gap. So that's if you accumulate that over k episodes, that's tell us the regret over these k episodes. Then for the constraint setting, we also need to look at the violation, because you can minimize the regret or even have negative regret if you violate the constraint, right? So therefore, not only the regret is important, also the constraint violation is important. Here again, we are looking at over this k episode, what's the total constraint violation, cumulative constraint violation. Okay, so for any policy, we're gonna use these 2 metrics to evaluate the performance. What's the regret and what's the constraint violation? Okay. So the problem has been studied now for like 4 or 5 years now. There's a lot of the literatures on that. Largely, we can divide the literature in these three categories. One is a model-based solution. That's probably the most straightforward one, right? Because we know how to solve the problem when the model is given. So let's divide the problem into two phases. The first phase is to collect data, estimate the model. Then I have the approximated LP. Then I solve the LP, get a policy. Then I use the policy to collect further data and to refine our model, then get under the policy and continue to do that, right? So that's the model-based solution. I can also, for the computation perspective, do a partial model-based solution, okay? Then I can use the primal dual algorithm. Then either in primal or dual algorithm, I use the model. The other part, I just update according to some algorithm. Okay, so that's the partial model-based solution here as well. Then the third solution says, okay, I don't want to use the model-based solution. I don't want to estimate the model. I want to use a data-driven approach, like use the policy gradient type algorithm. But let's assume we have a simulator. Like I can acquire data from any state, right, and take any action. Okay, so it's a simulator. I can configure the state of the simulator at any state I want, then get all the data I need. Then I use that to train my algorithm. Okay, so my view about that with the simulator is this problem. I mean, this approach is almost as expensive as getting the model, because to build a perfect simulator, you need to have a perfect model, right? If you don't have a perfect model, you cannot build a perfect simulator. Okay, so it's basically simpler, right? So at the time we look at this problem, there's no model-free approach, which means you just collect the data. And the data you collect is not like arbitrary data. You have to start from somewhere, actually apply the policy or take the action, then get the data result from that action. So you cannot like arbitrarily query any state and action. It have to be a valid trajectory, right? So there's no model-free and simulator-free algorithm with convergence guarantee and optimality guarantee at the time we look at it. Okay, so if we compare to the case like for MDPs, actually, even in back 1989, the famous Q-learning algorithm is a model-free algorithm with a provable convergence guarantee, right, by Watkins. So there's a huge gap, therefore, between the MDPs and the CMDPs in terms from reinforcement learning perspective. Okay, any question? Yeah.
Sorry, I came a little late. No, the next slide is probably better.
Okay.
Is the problem harder if the constraint is not in expectation but in probability? No, like
that's a good question. So I guess the probability, what kind of probability? If the probability is imposed, for example, per episode, I think it's harder. Okay. And if the probability is imposed per state and action, then you can translate that probability as the utility function as well. But if it's like for the entire episode, then it's harder. Yeah.
So there's no LP. Is it known whether it's an LP or not, or convex?
Oh, is that LP or not? That's a good question. I don't think it's as far as I know, there's no LP solution, but I could miss the literature. Yeah. Most of the LP solution is for this kind of average setting. Yeah. Any other questions? Yeah, I think if the constraint is even the hard constraint, if it's imposed on like the single state action for each step, it's actually relatively easy. But if it's imposed across episode, then become much harder. Again, because now you couple all the states, right, overlaps. Yeah. Okay. So just a quick reminder about what the problem we try to solve. We solve this constraint problem, try to maximize the reward subject to the utility constraint. Okay, so how do we do that? Okay, so now given this as a constraint problem, and like when we deal with constraint optimization problem, what do? We try to make it unconstrained, right? How do we make it? How do we make it unconstrained? We use the primal dual approach. We like add a Lagrange multiplier, take the constraint into the objective, and to form the primal problem. then we can update the Lagrange multiplier or the dual variable use subgradient method. So it's pretty standard, right? It's what we use for solving constraint optimization. Okay, so that's a standard approach. So what's the benefit of doing that? First of all, if we fix lambda, what happens is now, if you look at your primal problem, right? The primal problem is actually become an unconstrained MDP. If we regard this R plus lambda times G as your new reward signal, it's a combination between the reward and the utility, but nevertheless, just view that as your new reward signal. Then maximizing that objective is an MDP problem, right? It's the original, similar to the traditional. Then the dual update is also very straightforward. It's just a subgradient method. So collect the utility over the episode, then to see whether the constraint is violated. If the constraint is violated, you increase the dual variable by adding a higher penalty. Otherwise, you decrease that. Okay, it's pretty straightforward. So, but what's the challenge of applying this algorithm? Okay, so this algorithm would work in the case if we can fix lambda for a very long period of time and let the primal algorithm converge. Then we adjust lambda and then let it reconverge it again. Okay, but for doing that, remember the issue is if we do that, then every time the lambda is fixed, you are maximizing our objective, which is different from the original objective, right? In the original objective, I'm care about maximizing the reward, but now you are maximizing something else. So the regret will be different. Actually, if you fix lambda, the regret will goes linear, right? So will not give you a small regret. So your policy you get will be off from the optimal policy. And the second, remember, in the very simple bandit example, what I have illustrated is in most of those constraint cases, your policy is a stochastic policy. So that means if I fix lambda, okay, if I get an optimal policy from my primal problem, it will not be my optimal policy. The reason is if I fix lambda, if I solve the primal problem, I get a greedy policy. And the greedy policy is not optimal, that I know. Therefore, whatever the lambda you use, you cannot recover the optimal policy. Okay, and how do we recover the policy of the primal dual? Is by varying this lambda over time. So you have a distribution of lambda, and each lambda give you a greedy policy. You have a distribution of greedy policies, then you combine them together, then you get the optimal policy. Okay, but remember, for doing that, first you need to fix lambda for a long period of time to get a greedy policy, and then you vary that, right, and so on. So the convergence will happen very, very slowly. Okay, so that's the second part. Okay, so then therefore we need to design the algorithm very carefully to be able to minimize the regret and to be able to minimize the constraint variation as well. Okay, so that leads to the triple Q policy that actually was developed by my former student Hong Hao here. He is now assistant professor at Washington State, but he's still here in the audience. Okay. So it's called triple Q because it has 3 different Q values. One is the Q value for the reward. So that's the traditional Q value in the Q learning. Second is the Q value for the utility. That again is similar to the traditional Q value for the reward, but we replace the reward with the utility, but definitely the same. Okay. Then we have the third Q value, basically the dual variable, which we call the virtue Q. Later you will see why we call it virtue Q, because the dynamic of that Z is basically like the Q in the Q. Okay. So next, as I said, if we use the primal dual approach, we need to vary lambda slowly, compare with how we take actions in the primal problem. So the algorithm we need to implement in 2 time scale fashion. We will divide the episodes into frames, such that a frame has k to the power alpha episodes. Okay, then for within each frame, the Lagrange multiplier or the dual function is fixed. Then we solve an unconstrained Q-learning problem. Then we vary lambda at the beginning of each frame, and then solve another Q-learning problem, and so on. Okay, so the idea again, it's pretty straightforward. It's just a primal dual, but implemented in a 2-time scale fashion. Okay, so the interesting design component actually comes into these additional terms we need to add to make whole thing work. Okay, so first of all, in the primal algorithm, you cannot just use the traditional Q-length. You have to add something called the UCB bonus, right? The purpose of adding the UCB bonus is to make sure the Q table you get under the algorithm will become an overestimate of the Q value. So that will help us to bound the regret. Okay, so in addition to update the Q value based on the next state and the reward, you add this additional bonus term to guarantee overestimation. It's called optimism in online learning. Okay, so that need to be added. Then in the virtual Q case, when we update this dual variable, it's also not the traditional subgradient method. You need to add something which called a pessimistic tightness factor to intentionally make the constraint tighter. You will see why we have to do that. So guarantee small constraint violation. Okay. Then at the beginning of each frame, you again need to add some additional bonus term to guarantee overestimation. Okay.
What is capital C bar?
That's the average utility you received over one frame. Yeah. So each frame consists of multiple episodes. So the C bar is just the empirical total utility. So let me first tell you the result, then I'll tell you the analysis just very briefly. Okay. So the result is that by combining these components together, basically it's a 2-time scale algorithm, use the primal dual approach, but use the online learning part, the optimistic part for the primal problem, but use the pessimistic part for the subgradient for the dual update. If we choose those parameters carefully, what we can achieve is, first of all, sublinear regret. So the regret grows as a sublinear function of the episode length, grows at k to the power 0.8. And we also can guarantee a zero constraint violation on the average sense. So if k is large, then the constraint violation becomes 0. Okay. And the memory complexity, which means what are the values the algorithm need to remember, is at the order of S times A. So S is state space size, A is action space size. So that's basically the criteria used to judge whether the algorithm is a model-free algorithm or not. Okay. So for model-based algorithm, because you need to estimate all the transition kernels, so it will require S squared times A number of memory size. And for model-free, you only need S times A. So it's more scalable. Okay. Any question? Okay. So just some very briefly about the analysis. How do we bound the regret and what are the interesting ingredients in the analysis? So first of all, look at the definition of regret, right? Regret is the difference between the Q value at step 1, which tells me the reward I get for the entire episode, right? So Q value is the sum of the reward. So I look at the Q value at step 1 under the optimal policy, subtract the Q value at step 1 under the policy I use at episode K. Okay. However, this quantity is unknown because for any policy I used, I don't have an estimate of the true Q value. What I have is what the Q table tells me. And how do we update the Q table? The Q table is actually updated based on all the past policies, right? I'm not like run a policy for many episodes, try to estimate that. I run many different policies and continue to update my Q table. So that the Q table you have actually is not necessarily very close to the Q value you had at step K. Okay. So and also the Q pi K is unknown. So the first step is we need to add and subtract the Q estimate, that value in my Q table, into this equation. So now we can look at these two differences separately. So first, let's look at this difference, right? This difference basically is the estimation difference because QK1 is the estimate of Q1 pi K. So this is the Q table, the Q value I'm using at episode K. This is the true Q value of the policy used at absolute K. So the first one is estimated sigma, right? So therefore, this term is just estimation error of the TD learning algorithm, and we can control that by control the learning rate. Right? Control the learning rate alpha. Let me find you where the learning rate appears. The learning rate appears here. It says how quickly I'm updating my Q table based on the new information. Okay, so the estimation error can be controlled by choosing this learning rate differently. Okay, so if the learning rate is alpha, then the estimation error is K raised to the power 1.1 minus alpha over 2. There's some calculation behind it. Okay, so that's one. So now let's look at the first term, the first difference term, which is the difference between the Q value under the optimal policy versus the Q value I have recorded in my Q table, right? So what's the relation between two? So you can imagine these two may not be have some deterministic relation because one, if you are having accurate estimate, right? If Q is accurate, this is equal to pi K, then you can imagine the first term is larger than the second term because the first term is optimal policy and the second term is sum policy. So the first term should be larger. On the other hand, this is also not accurate because there's some estimation error here. So therefore, it's not clear whether the first term is larger than the second term or not. That's unclear, right? So that's the reason we added the UCB bonus. Remember, if you go back, we're adding the UCB bonus B here in the estimate. So make the estimate larger than what is necessary. So that's called optimism. What it does is if we add the estimate, like in the banded online learning case, use the UCB algorithm, you can guarantee this one. Okay, so I missed one step. Okay, before going that, the UCB bonus is added to the primal problem. The primal problem is try to maximize this objective of the Q value for the reward plus a weighted Q value for the utility, right? So we need to first reconstruct this term. Okay, so we need to add the utilitarian term into the Q value as well. And after that, you can show by adding this UCB optimism term, the second term will be larger than the first term. Okay, that's called optimism. So your estimation is always larger than the best estimation or the best policy is Q value. Okay, so therefore we can bound the this term to be negative. Okay, so this term is less than or equal to 0. So now we have all the remaining term because we're adding and subtracting this term. And also here, we are replacing the policy with the optimal policy, but the original term is with the policy with K. Okay. And interestingly, to analyze this residual term, we can look at the virtual Q value and look at the drift of this virtual Q value. By coincidence, somehow this term will become the drift of your virtual Q. Okay, because this is the drift of virtual Q, and you can ignore this term. Say this is greater equal to. Sorry, you can move this term to the left-hand side and then bound that. Okay, so I will skip the detail. The key here is whatever the residual term turns out to be the drift term of the Lyapunov function, like the difference between the Q from time 1 to time K. Okay, and we put this in, then we can bound the first term to be CK divided by eta. Here eta, you can see, is weight. The tuning parameter decide the weight of the Q value for the reward versus the Q value for the utility. So you balance the reward maximization and the constraint minimization. Okay, so there's eta. So we have several parameters here. The parameter regret, okay, is determined by this alpha learning rate and also this tuning parameter eta here. Okay, so we need to choose that, but not so quickly because we have constraint violation to worry about, right? So here we only consider regret, having looked into the constraint violation. So how to deal with the constraint violation? So for regret, like in the online learning literature or in the reinforcement learning literature, we know regret can be analyzed using kind of bandit type analysis, use the concentration result. So how about constraint violation, right? How do we understand constraint violation? So let's look at actually the virtual queue dynamic. Okay, so now let me explain why it is like a virtual queue. So remember the dual variable is updated based on z plus rho minus c, okay? So now think about this as a queuing system, right? And the customer come in with rate rho, and the departure from the system with rate c bar, okay? And if you look at such a queuing system and write down the queue length, then it's exactly same as the virtual queue update. So that's why we call it virtual queue, okay? And why this virtual queue is nice? Because now we can use like the linear recursion. Basically, it's a recursive way to write out what this zk look like and get a lower bound. It turns out that this zk is upper bound on summation of this rho minus c bar. Okay, and what is this summation rho minus c bar? It is exactly the constraint violation. So which means if we are maintaining this virtual queue, then the length of this virtual queue is always an upper bound on the constraint violation. So the length of this virtual queue tells you the magnitude of constraint violation. Okay, so I can use the length of this virtual queue to evaluate the constraint violation. Okay, so now a little bit about queuing theory. For those of you have taken the queuing theory or at least have some experience with queuing, you know in queuing, if we increase the arrival rate rho, okay, then the queue length increase quickly when rho is close to capacity. So it's originally it's small, but when it's close to capacity, it will shoot up. Okay. So that actually become interesting for our case because remember, in the primal algorithm, the decision is based on the Q value for the reward and the Q value for the utility weighted by this term, right? And you can imagine like when I'm making the right decision, I have to have the right combination between the Q value for the reward and the Q value for the utility. If this term becomes 0, or if this weight is too small, I'm ignoring the constraint. If this weight becomes too large, then I'm ignoring the reward. Okay, so therefore the proper magnitude or proper order of this eta, the proper order of this my Q length has to match this eta. Okay, so this one cannot go to 0 or infinity. Z divided by eta has to be some constant, right? To make sure like the algorithm take into account both the reward and the constraint violation. Okay, that also means I have to drive up my Q length to eta, which is in our final choice is k to the power 0.2 to make sure the algorithm work properly. Okay, that also means the constraint violation will be at an order of k to the 0.2. Okay, but that for us, we're thinking about this is sublinear. Can we make it better, right? Can we drive down this constraint violation for the applications where maybe violation is reduce the violation is more important than maximize the reward? It turns out you can, and it turns out you can do that almost for free in the order sense, right? It won't affect your regret order, but we can dramatically reduce the constraint violation order. The idea is, as I mentioned in the algorithm, to add this pessimistic tightness factor, okay? So basically say, okay, I'll add this additional epsilon, right, to my arrival. So it's not the true arrival, it's some like virtual arrival, try to make your system as like a more busy than it look like, okay? So what happens then? What happens is now you can drive up your Q length, right? Drive up your Z, but your constraint violation is still small. Why? Because again, you use the linear recursion. What you have is now the upper bound on the constraint violation becomes Z minus epsilon times a function of K, okay? So you can still have large Z, which is not needed for balance reward maximization and constraint violation, but you can make your constraint small by choosing this alpha and epsilon property, right? So you can even drive down that to 0 on the expectation sense, okay? So this is actually the idea used on the internet back to like 2000. People try to do congestion control, but the problem of congestion control originally is you have to see packet loss to see the network is congested to reduce the transmission rate. But when the packet get lost, the network already congested, So what do? Is we make the link capacity smaller than is what necessary and maintain some virtual queue. So when the virtual queue is large, it means it start to get congested, but not yet, but you start to send the congestion signal to that. Okay, so that's exactly the same idea. Make the constraint violation Z, the Q length indicator, is larger than the true constraint violation. So my algorithm can kind of proactively take action to be conservative before the constraint actually is violated. Okay, so that's the old idea, but the new use of that. And at the end, you get the violation actually become this eta minus this. Okay, so now if you optimize that, what eventually you can get is this regret, this is the violation, and you can make sure the violation becomes 0, but the constraint violation becomes 0.8. One interesting fact is, in fact, even you allow a higher constraint violation, as long as it's not linear, you cannot improve regret. So the regret is always same order, but by doing that, you get like 3 smaller constraint violations because the violation becomes an additive term. It's not a multiplicative term for the regret. So as long as what you bring from the violation to the regret is smaller order than the original regret, you get that for free in the order sense, right? It's not really free, but order-wise, the impact the regret. Okay, so that's the algorithm. That's how the algorithm works in one of the environment. This is the existing algorithm, and here we implement in the neural network case. You can see it works pretty well. Okay. Okay. So any question? So now let's see. We further extended the algorithm to infinite horizon average reward case and the non-stationary case. We get sublinear regret and the constraint violation as well. Okay, so I still have 10 minutes. Let me ask you, anyone see the problem of that algorithm? I tell you all the nice things about the algorithm, but the algorithm actually is not that ideal. Anyone can point out why?
Computational reasons?
Yeah, computation is one, but there are other reasons. First of all, the regret is not optimal in the order sense because we know if we use model-based solution, we get a K regret. But that's just a theoretical part. The practical part, one is computation, another is it never gives you the optimal policy, right? You can see in the update the lambda continue to change, your Q table continue to change. You never get actually a policy. You get something like in the online learning case continue to vary. It just says at the end, if you look at average, you get a good policy by average all possible policies there, right? So the way people to extract a policy from this kind of algorithm, it says, I remember all the past policies. Then I randomly sample one. Then on average, it's a good policy, but you know it's on average, right? So with some probability, you get a very bad policy as well. Okay, so that give you an optimal policy. So that's why we are interested in asking the next question. First of all, is it possible to reduce the regret to meet this lower bound? Second, can we actually do best policy identification instead of regret minimization and to get the best policy, get a single policy, which is stochastic policy, but it's a single policy, right? It's not sampled from a gigantic number of policies, right?
Ask a clarification.
Yeah.
Question. So if it's not giving you a policy when you define regret, regret is the regret of what?
Regret of all the policy have used over the K epsilons.
Average over, like average worst case over all policies?
On the expectation sense, like you sum up over all the policy used over the K epsilon, that's their regret.
Summing up all
Yeah.
over K.
Right. Yeah. So the regret is small, but you don't get the policy. Yeah, right. Yeah. Okay, so to answer this question, now let's go back to some basics. Again, the LP. You ask a question, right? The problem is harder, I know, but how much harder it is, right? I know now I go from greedy to stochastic policy. That's the main reason. Now the problem become harder, right? But if you look at the LP perspective, you always puzzling, right? It's still an LP, right? Without constraints, this term disappears, but it's still LP, right? For the LP perspective, for single constraint, you're just adding one more linear constraint. Why is things so different, right? Let's look at actually more general case. Let's say instead of one constraint, we have a capital N constraints, right? A finite number of constraints. Right? Let's look at this LP again. Okay, so let's do linear programming one. Okay, let's look at. So I mean, this is not a new result. This result established back in 1980s, but it's a very interesting observation we are able to leverage. Okay, so let's do LP11. Say this is linear programming, and how many decision variables we have. The decision variable here is related to it's the occupancy measure, indexed by the steps, state space, and the action, right? So the number of decision variable we have is H times S times A. Okay. Then how many constraints we have? We have N constraint from the first inequality. We have S times H minus 1 from the global balance equation. We have S constraint for the initial condition. Then we have H times S times A from the constraint like the Q has to be greater equal to 0. Okay, is that clear? I'm just doing the counting, right? How many variables we have, how many constraints we have. Okay, believe me, all the numbers are correct. Okay. So now from LP, we know one of the optimal solution will be an extreme point. Okay, so now if we look at that optimal solution as an extreme point, we know that solution has to activate H times S times A equalities, right? Because at extreme point, I have this number of variables. I need this number of equalities to uniquely determine these variables. Okay, okay, that is again, it's very basic, right? So now I ask question like, very interestingly, how many equalities I need to get from these inequalities? Okay, that's the interesting question. So let's look at that. So I can get at most N equalities from the first inequality. I can get at most S times H minus 1 from the second one. I can get at most S from the third one, right? So how many equalities I need to get from the last one will be the total number I need minus upper bound the most I can get from the first 3 ones. That will be the number of equalities I need from the last inequalities. Why I'm interested in that? Because every this equality tells me this occupancy measure is 0, which means I don't do anything there. I don't take that action, right? There I need to take a greedy division, right? So it turns out the number of non-zero measures is H times S plus N, okay? That means, let me actually directly go to the conclusion, is for the optimal policy, which corresponding to the extreme point, I only need to take N stochastic decisions. Okay, so if N is 0, which means greedy policy is optimal. If N is 1, if I only one constraint, I only need to find one state, randomize that. I don't need to care about other states, other actions. That will give me the optimal policy. If I have 2 constraints, I just need to locate 2 places, 2 states, randomize my action, and that's enough. Okay, so that says if the N is small, the number of randomness you have, that's called the number of randomness in the book, is small. Okay, so that actually haven't been leveraged in the reinforcement learning CMDP literature, but it's a very important property because now you can imagine what we can do. What we can do is maybe we can find a policy by doing this in 2 phases, right? The first phase is to locate where the stochastic decision has to be taken. Okay, I locate the state and the step such that at that step and the state, I need to randomize my action. That also means for all the other places, I just take greedy action, then I can use the traditional like Q-learning type algorithm, right? So then the next question is, after you locate these stochastic decisions, how do you determine the proper randomization of the distribution? Okay, so we should leverage that, and the way to leverage that actually is based on some sublinear regret and constraint violation algorithm. So it's not like completely new algorithm, it's built based on the triple Q, but help us to solve the 2 problems I mentioned. One is the regret can be further reduced. Second is you can get the policy, right? So how do we get that? Okay, so let's go to the first question. Before that, any question about what are the questions we try to answer? Okay, so first, how to locate this stochastic decision? Because if you look at the Markov chain, you have like H steps. At each step, you possibly have S states. So you have a total H times S locations, right? To randomize. So if n equal to 1 or 2, you need to pick like 1 or 2 from this number. So it's combinatorically, if you try each of the combination, it's not a easy problem, right? But imagine you already have a model-free algorithm, which have you give you a sublinear regret and a constraint violation. What it tells me is this algorithm, right? When we look at the number of actions, so like the frequency of the actions taken in each state, if that state you take greedy actions, then under this algorithm, that action has to be taken majority of times. Because otherwise you are making suboptimal decisions for constant fraction time, then you cannot get a small regret, right? So if you have a low regret algorithm, then for the locations or the states where the greedy decision has to be made, you are basically most of the time are taking the greedy decision. So the way to leverage this is now I can run the triple Q algorithm for square the K episodes. Then I look at the frequency and I look at at particular state, whether this action, what's the percentage that action has been taken. If that percentage is too small, I say it should not be used, okay? If the percentage is close to 1, I say, okay, now I set this to be 1, and that is the greedy, the state I take greedy decisions. So interestingly, the problem is also intuitive. So if I give you a problem, I say, how to say that? Okay, yeah. So in this step, basically what we are doing is a classification. We try to classify whether that state is greedy or stochastic, right? But in the original problem, what we need to learn is a policy. So we need to learn the exact distribution. So therefore, do the classification is much easier because I just need to tell this is greedy or stochastic. I don't need to figure out the exact frequency the action has been taken. So therefore, if I just run the algorithm for square root of K time, it already allows me to do this classification very, very accurate. So in the first step, I can with high probability to distinguish greedy decisions versus stochastic decisions and narrow down those small number of stochastic decisions. So the next question is now greedies are fine, right? I know what exact greedy decisions to take. For stochastic decision, I still need to determine the distribution, right? It's like 0.5, 0.5, 0.2, 0.8. How do I do that? For doing that, actually, we use the following lemma. So we say any stochastic policy with n stochastic decisions can be equivalently thought as a linear combination of the 2 to the n greedy policies, right? So you have one state, you can take 2 possible actions, you construct 2 policy. One policy take action 1, the other policy take action 2. So you can construct like 2 to the n at most greedy policies. And in fact, the occupancy measure of the stochastic policy can be thought as a linear combination of the occupancy measure of these 2 to n greedy policies. So now from the first step, I already know what are these 2 to the n greedy policies, right? So in the step 2, what I can do is I can do the policy evaluation. I fix all these policies. I estimate the reward value function and the utility value function. Then I solve this constraint problem, right? The constraint problem basically is the original problem I try to solve, but now I narrow down my optimization parameter is just the weight of different policies, right? So I can do that. I can iteratively do that. So I can first do the policy evaluation, then solve the A. Then I apply the A I solved from the solution, which give me how frequent I should use each individual policy. Then I further collect data. Then I re-solve this problem, get a better A, and so on. And eventually, I'll get a set of weights which close to the optimal solution. Okay.
One question. I think it should be convex combination, right?
No, all these are numbered, right? So if a policy is given, I'm learning the value function for that reward value function for that policy.
Oh, right.
Yeah.
Learning the
Yeah.
reward value function
So
instead of the policy.
Yeah. So in this optimization problem, these are all numbers. These are the variables you optimize.
Repeat, how do we solve this? I mean, where do we get 1 pi m from here?
In the previous step, right, I'm able to identify the greedy decision and the stochastic decision.
Yes.
For the stochastic decision, I know like which action should be involved in the stochastic decision to randomize. So therefore, if I just take a combination of the greedy decision with one of the stochastic decision, that give me one greedy policy. And if I try all the combinations, at most 2 to n of them, I get all possible greedy policies, right? Because n is small, then, I mean, n is large, that's a different story. When n is small, then I have a small number of greedy policies. Yeah, so again, one thing I want to emphasize, this is model free. Nowhere I need to learn the model. I basically just use the data to get that, right? But still, I don't want to get like 2 to the n policy and get a weight for me to use, right? I want to get one stochastic policy. The idea is very simple. You run that, then you measure the empirical occupancy measure from the LP, again, from occupancy measure, you can recover just one stochastic policy, which is almost optimal. Just 1 minute, okay? The main result is you can achieve this h times squared decay, regret, and constraint violation. Memory capacity, complexity same. I want to point out the different from the triple Q, these regret the independent of state space size, action space size. Actually, it's very scalable compared to the other. And it's in output of one policy, and the policy is accurate with high probability as all greedy decisions, and very close to the true optimal policy at stochastic decisions, and it's based on, I mean, how accurate based on the number of episodes we have. It's just some simulation. It's very simple synthetic simulation, and the number I want to focus on is this on this table. This is a solution from optimal policy, and this is what we get. Okay, so we get a policy. The performance is extremely close to the optimal policy for stochastic policy. These are the publications, and these are my collaborators. I think I'll end it here to answer any question.
So first of all, yeah, thanks for the talk. And I see that there is a question on the chat.
Yeah, right. Yeah, how large the K yeah, there are some condition in the paper specify the K or how large the K. The K is pretty large. It's not a small number. Yeah. Yeah, I don't remember exactly how large the K should.
I have also a quick question in terms of the computational complexity per step, right? Is it? I suspect it's polynomial. Or you have still like some kind of Kershaw dimensionality? What's the case here?
Yeah, I think I made a mistake when I made a comment. Actually, the computation complexity for the triple Q is very low.
Okay.
Because you only need to update the Q table each time you just update it once.
Okay.
Right. It's not that complicated. Thanks. The computation complex come from you need to run the episode for a fairly long time.
Okay.
Yeah. So for each step is long. Yeah.
Okay. Thank you. And any other questions?
Yeah.
I'm not familiar with any of these regret bounds. Like, what in the unconstrained case with the regret that we get from like one of the mainstream algorithms?
So if you use the optimistic Q-learning, you get a squared K regret. Squared K is also a lower bound. Yeah. So and in the primal part, we basically use the optimistic Q-learning too, but we didn't get the same regret because we need to modify the. I mean, it's not the original reward, right? It's a reward plus utility. So that's.
The regret independent from the state space. In that case, can you just augment the state space under some like discretization?
Sorry.
To keep track of these constraints, augment the state space, and in the unconstrained case, if the regret is independent of the size of the state space.
Oh, it's not. It's depend on size of the state space. Yeah. Usually.
The rest is same, and it's just square root of K. You said that the regret is square root of K, right?
Yeah. So I mean, in terms of like scaling in terms of K is square root of K, but there's dependence on the episode length, state space size, action space size as well. Yeah, but for tabular case, usually we say state space, action space finite, and the K could be a large number. So we mainly care about, not mainly, but lots of the focus is on the scaling in terms of the number of episodes you have, how long you need to run the experiment to learn that. Yeah. Yeah.
So,
Sorry, I'll come back to you. Yeah.
the violation is total up. So the method can essentially alternate between really violating and really not violating. And on an average, it will sort of.
Yeah, yeah, right.
Sense of does it like if I measure the positive part of the violation, how would the method?
Yeah, so that's related to a different constraint violation metrics we evaluate. That's a very good question because you can have like negative 1,000, positive 1,000, the average is still 0, right? So here we are measuring the average. It's more like a budget type of constraint. You can put like a plus sign there, say the negative doesn't count is always 0. I only count the positive part. Then I think we need to use a different algorithm. The exact algorithm will not work in that case. Yeah.
Right. The first one is just a clarification.
Uh-huh.
I think in slide 30.
30? Okay.
Show the LP with the CMDP.
LP?
When you show the LP for the CMDP.
This one?
Yeah. I just wanted to confirm that these constraints by themselves, they constrain that the sum over the state occupancy for its over all states and action over a horizon should sum to 1.
Yeah, right. The reason is because it'll sum up to 1 under the initial condition. Yeah, then you have the transition. Yeah, so that's just.
I think has to do with the constraint violation.
Uh-huh.
Eventually, if I choose a policy which doesn't do anything, I achieve zero constraint violation, but my regret is exponentially large.
Uh-huh.
And in that case, one of your solutions was adding a pessimism into your constraint violation, and then you showed how this led to the.
If you have policy which do nothing, then your reward will be low, right?
Exactly.
Yeah, so in the regret part, we have the reward plus the constraint value utility. Yeah.
So my question is basically when you are adding this pessimism to your virtual queue, this epsilon, is this leading to overly conservative policies while running the algorithm?
Depends on how large the epsilon is, right? So if you don't choose, it's hyperparameter. So you have to choose.
Sensitive to epsilon?
It is, yeah, and it has to be chosen as a function of k, right? So a function of k, yeah. So practically, you ask me like how large the epsilon is. I don't know. You have to run the experiment to control that. It's a hyperparameter.
One more question.
Yeah.
Yeah, I will ask, this is more maybe not related, but in general, when we talk about partially observable Markov decision processes, where we do not observe the state, usually we are dealing with the uncountable states.
Right.
Do you have an idea of what kind of analysis would go there? For example, many papers and many works in the line of reinforcement learning are related to Q learning in the tabular setting. If you have any thoughts on somebody who is working with POM-DPs or.
Yeah, so POM-DP hard, right? POM-DP hard because even the model is known is hard. Yes, and if you remove the no model, have to learn that, it becomes even harder. Yeah, I think
this in the second iteration of your triple QL algorithm, you said that the computational complexity is independent of state and action space sizes. It's only the memory part of it is still dependent.
Right. Yeah. It's partially true. Okay, so I have to again correct myself here. It's independent of the k when k is large enough. That's right. So and the threshold when it becomes independent based on k.
Can you repeat?
So the function, you can look at function, right? The function is independent of s only after a certain threshold, only when k is large enough.
Right.
And that threshold depends on the state space and action space size. So if you make it uncountable, then you cannot find such point. Right. Yeah. And also different from POM-DP, I think there's some similarity in a sense. For POM-DP, again, you go from finite to uncountable, right? By into the belief state. But you don't have this limited stochasticity in POM-DP. Every state become continuous. So here, the advantage, the one property we took advantage of is the limited stochasticity. You know only a few places you need to randomize and just focus on that. But for POM-DP, everything becomes continuous. Yeah.
It's either for POM-DPs, the problem will change if your constraints are on the observed part versus unobserved part.
Definitely.
That will make a difference.
Definitely. Yeah, but one thing maybe you want to look into is the POM-DP also have LP type of formulation. So maybe just look at this LP to see what special property. I believe people have looked at that, but worth looking at again, right? Yeah. Yeah.
Thank you.
Yeah.
Yeah, I think what was the question that we answered already.
Oh, okay.
That's okay, I can help you.
Oh, okay.